Hello students, welcome to the lecture series of DC machines and transformers. Today in this session we are going to discuss about the speed control of DC series motor. Already we have discussed about the speed control of DC shunt motor. So here in DC series motor speed control, first method is rheostatic control method. For this method, rheostat is to be connected in series with the motor so that that control resistor, if you change that control resistor RC, you can control the speed of the series motor. In this method, if RC is equal to 0, you will get a speed, and if you change the value of RC, you can reduce the speed, meaning that if you are increasing the resistance, the current is reduced and so the flux is reduced. So the controlling of control resistor which is in series with the motor will make the speed control here. In the armature diverter method, one variable resistor connected across the armature alone. So we are diverting the armature current. The IA is reduced due to armature diverter, so that the flux must increase because TA is proportional to pi IA. This results more current taken from the supply, hence the flux is increasing and the speed is decreasing. Speed is inversely proportional to the flux. So this variation in speed is by varying the diverter resistance. When we change the diverter resistance, the current flowing through the armature is changing, and that makes the flux, that alters the flux, that varies the flux. So when flux is changing, the speed is changing. This is armature diverter. In a field control method, we are connecting a rheostat across the field winding. Here the field current alone diverted, not the armature current. Field current alone diverted using field control method. Based on the RD value, current flowing through the series field winding is controlled, is varied, and the flux is varied, so that the speed is varied. So there is field control method. In field control method, we have other different arrangements. That is the tapped field system. While designing itself, the field winding is having number of tappings. So if we connect tap 1, it gives some flux, and the tap 2 some other flux, tap 3 is some more flux. So the different flux can be created by connecting different tappings of field, maybe the full field flux or a partial field flux, 25%, 30%, based on the tappings taken from the field winding, the flux will be changed. Another thing in field control method is paralleling of field coils. Instead of having a single coil, we can have 2 coils or 4 coils in the field winding. Here in this example, we have 4 coils. So the 4 coils can be connected in series so that it will give you some flux. So all the coils will get the same current. So the flux will be 4 different fluxes of same amount, which will be there for running the motor. And in the same 4 different coils which can be connected in parallel, and in other case 2 as series, another to a series, that combination can be a parallel. So in that case, the current will be different. And if you still want to control the speed, you can put one field diverter with the combination, parallel combination of field winding. So this is another way of controlling speed in DC series motor using field control method. And the series parallel connection of series motor, two series motors taken, both can be connected in cascade or both can be connected in parallel with the supply, so that if it is connected in series, both will be having the same current flowing, so that it is running at rated speed, but the voltage is off. So when voltage changes, there also speed is changing, since V minus Ia or A by pi, right? And if it is in parallel, the current is changing in both the cases, right? Parallel series connection of motors, two motors, will make changes in the speed. So this type of method are used in electric traction applications. So in a series parallel, when in parallel, N is proportional to EB by pi and N is proportional to EB by I. I is the current through the series motor. There is only one current, field current, line current or armature current. All the currents are same in series, since it is series. N is proportional to V by I by 2, and which is proportional to V by 2V by I. And we know that torque is proportional to pi Ia, which is now becomes I square, so that I is I by 2 whole square, so I square by 4. So when in series, see that when in series, if you find the torque which is proportional to I square, so the torque is 4 times that produced by motors when in parallel. So when in parallel, the torque is proportional to I square by 4. When in series, it is proportional to I square. So in a series connection, the torque is 4 times that produced by the motors when in parallel. So in a speed control method, there are merits and demerits for rheostatic control. Large amount of power is wasted in control resistor. In rheostatic control, we are dissipating the power as a heat through the rheostats. So the loss of power is directly proportional to reduction in speed, hence efficiency is decreased. And it needs expensive arrangement. You require a rheostat which has high rating based on the motor's current rating, and gives speed below the rated speed. And in a field control method, there are some advantages, like more economical and efficient method used to control speed above the rated speeds. Only drawback here is effect of armature reaction. Effect of armature reaction is more in weaker field. Thank you. That's about speed control of DC machines in series motors.